I brought this because I like it.
Well, hang on, you've just...
No, I like it. This is brilliant, but I like this.
Today, we're back with another deep dive. It's been a while, and forgive me for that, but things have been a bit interesting in the good old US of A. During my absence, I got a new M-chip MacBook, so no more complaining about that old Intel CPU. With the new hardware, I wanted to dive into higher performance native code. So let's talk about Rust, but don't worry, we're not giving up on Python just yet. First, why Rust? Well, for general purpose programming, there's a ton of options. And while we are going to do general programming, we're not going to do only general programming. Plus, with a focus on machine learning that really narrows the field. Python, maybe surprisingly, is out. Yes, most of the big machine learning libraries are Python. However, most of the time the performance critical code is just calling C++ or something else under the hood. And calling C++ from another language isn't really what I had in mind. You'll see why in a second. So Python is out, as is anything in that ballpark. Go is also out. For one thing, it's got a garbage collector, and garbage collection could be a whole nother video. But in short, it causes performance unpredictability. Also, Go isn't really that big for machine learning anyway, and some of the design decisions didn't really appeal to me. Then there's Zig, which seems interesting, but it's still young, and it doesn't have quite the same focus on safety that Rust does. In the end, we're left with two paths. Coke or Pepsi, Vim or Emacs, Rust, or C++. Both Rust and C++ are fast. They're generating native code without the need for a VM or runtime. They're also statically typed with compile time optimizations. And they both have manual memory management, so nothing's happening at runtime, though there are some helpers. And you also have foundational ML libraries, like Candle or libtorch. Both have cross-platform support and language interop. On paper, either could work, but there's a few things that come to mind that set them apart. On the plus side for C++, say that 10 times fast, you've got a massive ecosystem because it's pretty much the industry standard. It's also an incredibly flexible language, and sky's the limit when it comes to performance. On the downsides, when compared to Rust, I'd say it doesn't have the same strictness when it comes to safety, and the tooling isn't as good. But that's getting better every day. Also, given how old the language is, there's different dialects, so you have some legacy baggage. Lastly, I'd argue C++'s complexity is more implicit and hidden. So you've got some footguns there, whereas Rust I think is more explicit and upfront. On the plus side for Rust, I think for one, it's a very confidence-inspiring language. You've got memory safety and a powerful compiler. It's true that garbage collected languages are generally memory safe as well, but Rust is able to do this at compile time. Also, the compiler is able to catch all kinds of bugs, like missing fields and mutability and errors, and all of that happens before it reaches runtime. Rust is also a modern language with top-tier tooling. Cargo is one of the best package managers I've used. You've also got automated documentation generation and integrated testing. Not to mention you've got linting and formatting tools as well. But on the downside, it does have a pretty steep learning curve. Coming from the web world, there was a few concepts and paradigms that took me a little bit to get the hang of. Also, that powerful compiler I mentioned can be pretty strict and pedantic. The ecosystem also isn't as mature and broad as, say, C++, and while this is subjective, the syntax can be not as pretty as other languages. Ultimately, there isn't a wrong choice, it's just about what's the right choice for you. And for me, I felt that was Rust. Sure, I'd have to suffer through learning it, but in any case, it had been years since I had touched C++. My bet was that once I got the hang of Rust, I could work on more ambitious projects, and I'd have more confidence in the code I was writing. And I think that bet paid off. Also, I could write my entire stack in Rust, and I felt better about that than doing it in C++. Going back to my comment about not wanting to call C++ from Python, the goal here is to learn and dive deep, and just calling some interfaces or some bindings from Python didn't really seem to be in the spirit of that. So let's talk about Rust and getting started with it and some tips, and then walk through converting a Python app to Rust. Let's get up and running with Rust. First, go ahead and install Rust. You can find the instructions on the website. Go ahead and stick with the official installer instead of say Homebrew, as the Homebrew install can sometimes cause conflicts with other projects. While you're at it, you should go ahead and get the tooling set up. Rust's VS Code integration is really great. It has auto-formatting, IntelliSense, and other things. And eventually, try turning on Clippy for linting and best practices recommendations. And then, once you're ready to go, it's time to read through the Rust book. Sorry, there's no shortcuts with this one. Going from Python to Ruby, you could wing it and fill in the gaps as you run into them, but for Rust, you should really invest the time up front. After you've read the book, prepare for a month or two of pain as you get used to the Rustisms. Finally, you'll be ready to incessantly proselytize the good word of our Lord and Savior, Ferris. And fear not, here are some tips to help you along the way. In Rust, correctness is opt-out, not opt-in. In other languages, you have to actively choose to handle edge cases like null or errors, check return values, and consider all branches. Rust, on the other hand, flips this. The compiler forces you to be correct by default, and you have to explicitly opt out. This may sound like a burden compared to, say, TypeScript's gradual opt-in nature, and it is, but after you get the hang of it, it isn't that much slower productivity-wise. Of course, knocking out a simple script or demo is going to be faster to produce in TypeScript than, say, Rust. It just is. But the upside is Rust is immensely easier to refactor, maintain, and debug, and for production projects, that's a pretty good trade-off. Now, Rust module system can be tricky to understand because other languages conflate and abstract away some of the details. For a module system, there's roughly 3 parts. There's the file system, which has the files on disk. There's the logical module tree, which has namespaces and the like. And there's the import and bindings, which brings things into the current scope. Many languages, like TypeScript for example, consolidate these. A file is a module, and an import loads and binds things. Easy peasy, lemon squeezy. Rust, however, wants you to handle each of these pieces individually. Let's take a look at a TypeScript example first. In TypeScript, we have a foo.ts file that is implicitly a module. We then export a function, and then we can import that function from that module into our main file. Rust, however, separates these steps. There's the files on the file system. There's the pub mod foo, which declares the module into the logical module tree for compile time. And then there's the use foobar statement that binds it into the current scope. Rust forces 2 explicit steps, declaring a module versus binding, that other languages hide. That explicitness gives clearer compile time structure and predictable resolution. Also note how visibility is explicit. The use statement cannot make something visible if it's not declared as public. And the file layout matters too. Mod foo expects a source foo.rs or a source foo mod.rs. The module tree and file paths are explicit. Lastly, there's some common gotchas. Maybe you forgot a mod statement, so the item is not in the module tree. Maybe you forgot a public statement or other visibility modifier, so the item is not accessible. And here's a quick overview of the 2 allowed module layouts on the file system in Rust. Let's go over Rust's Typesystem. Rust Typesystem doesn't just shape or categorize data, It encodes ownership, lifetimes, and memory layout information, among other things. While this makes the language more verbose and complex, it also prevents entire classes of bugs, including memory safety ones, that other languages allow. Since Rust's type system is expressive and the compiler enforces type constraints strictly, you can use the type system to encode the semantics of your business logic into your types. For example, you have a type for your inventory order management system, and the compiler will enforce the various states. You can't ship an unpaid order or deliver an unshipped order. You're going to need to know stack versus heap memory, as different types use stack versus heap, and that determines where the data lives, how it's moved, and when it's dropped. Ownership is, in simple terms, who owns and will drop the data. Then, when you move, you reassign that ownership. A borrow is a temporary read or exclusive write access. Note, you can only have one thing with write access at a time, but you can have multiple readers. Lifetimes are just a way to specify and check the validity of borrows. Note that they are only compile time checks, and they don't change the memory management behavior. Technically, all borrows have lifetimes. It's just sometimes you'll have to explicitly write it, though most of the time the compiler can infer it. The syntax can look a little weird, but it's just a label to help the compiler verify safety. It's kind of like the label syntax for generics, and it can be whatever you want, but people typically choose a single letter for terseness. For commonly used collections, we have arrays, vecs, and tuples. Arrays being a fixed size collection of the same type and stack allocated, so the size must be known at compile time. Then we have vecs, which are growable collections of the same type and heap allocated, so they can be dynamically sized. Vecs are similar to array or list in other languages. Then there's tuples, fixed size, but can be mixed types, so they're similar to other languages. And then there's strings. And oh boy, Rust does not hold your hand. Note that a slice refers to a contiguous sequence of elements in a collection. First, we have string slices, which is an immutable reference to text, sort of like an array of UTF-8 text. Then we have string, which is a growable and heap allocated collection, sort of like a vec of U8 bytes with UTF-8 guarantees. Note that you can convert between the two with toString and as str. And then there's character encoding, and Rust doesn't hold your hand on that either. For example, .len is bytes, not characters. So e.len would be 2 for 2 bytes in UTF-8. And to get the nth character of a string, well, in other languages it works as expected, but Rust doesn't do that. Do you want the nth byte, nth Unicode, nth grapheme cluster for user-perceived character? Instead, you have to handle that explicitly. Enums are not just named constants, but rather sum types. In other words, the sum of different types, and each variant can carry its own data. And when you have an enum, the compiler will force you to check all possible variants or opt out. Enums are the backbone of many of the language's constructs. We have option enum for handling null data, result enum for handling recoverable errors, Under the hood, option and result aren't magic, they're just enums, but they do lead to some paradigm shifts. Most languages have null and also implicit null. In JavaScript, for example, you can set a value to null. You can also make a function argument null and omit it when you call the function. Rust, however, doesn't really have null, and let's skip over pointers and unsafe for now. In Rust, you use the option enum and you choose some value or none. And none is sort of like null, but it's an option variant, not a language keyword. So if you want to say a function argument is null, you wouldn't omit it. Rather, you would actually pass the none value. This makes nullability explicit and visible at every call site. Other languages have a traditional exception model for recoverable error handling. In simple terms, it's hope for the best, catch exceptions if something goes wrong. But that has hidden failure points, and you can't tell what might fail at a glance. In Rust, you have the result enum, which is either OK result or error E. Note that this makes it part of the type signature. This makes it explicit and upfront, acknowledge that things can fail. This also means you must handle each explicitly or opt out. So you eliminate production bugs from unhandled exceptions. This is more of a functional approach. Errors are values, not control flow. That said, Rust does have panics for unrecoverable errors, but use only when necessary. Speaking of errors, they're usually just enums with different variants that implement the needed error traits. Each variant can carry different data. Some might wrap other error types, others might just carry simple data like strings. And the this error crate makes building custom errors easier. Let's talk about some shortcuts and syntactic sugar. Unwrap is used with option and result to extract the value and not handle none or errors. In other words, I know this will work, just give me the value. Use it sparingly and mainly for prototyping because you're assuming you're always on the happy path. The question mark or error propagation operator is used with result enums. It's syntactic sugar for early returns in the case of an error. You can kind of think of it like a guard clause. The anyhow crate simplifies error handling. It makes error handling easier by providing a single error type that can represent any error that implements the standard error trait. It provides a uniform interface compared to having to handle different error variants individually. You should use it in application code, but not libraries, because it erases the detailed error information. Option and result can feel verbose initially, but they eliminate bugs where nulls weren't checked or exceptions weren't properly handled, so you can catch things early. First things first, structs, while similar, are not classes. Data definition is separate from method implementation. By separating data and behavior, it keeps types minimal and stable while letting you layer on behavior, privacy, polymorphism explicitly and safely. Note that the implementation blocks can be in different files from the struct definition. The trait system allows you to specify and implement behaviors on types. Keep in mind you can implement traits on your types or your traits on other types, but not traits you don't own on types you don't own. To recap, struct for data, implementation for behavior, traits for interfaces and polymorphism, composition, not inheritance, and ownership and borrowing for safety. References make borrowing explicit. Ownership rules are checked and enforced at compile time, which then prevents data races. References are pointers under the hood, but different than raw pointers, or what you might think of as pointers from other languages. And you can dereference to get the actual value. Args, or atomically reference counted, is for shared ownership across threads. Note that arg clone does not actually copy the data, it just adds another reference count. For example, let's say you want to load a memory-hungry ML model and don't want to create a new version of it for every request. You can use arg to safely share it. Generics are how to handle code reuse with strict types. It bridges the gap from dynamic languages. Generics and traits let a function say, "I'll accept any type that implements this trait." That gives similar flexibility as duck typing, but checked at compile time. Note that async is not actually baked into the core language. So unlike other languages, async is supported through libraries. Tokyo is the de facto async runtime for now. Also, Rust doesn't have green threads, also known as fibers. This is a design trade-off for lower runtime overhead. Here are some more general tips. First, it's okay when you're starting to use string and vex instead of string slices and arrays. Also, go ahead and use toString and clone. Coming from Python and the like, you're used to allocations anyway. When you're prototyping, use unwrap instead of proper error handling. And then later on, it's easy to search for clones and unwraps and similar calls to refactor. Lastly, most of the time, arguments should be references and return values should be owned. But to sum it up, just get it compiling first. Speaking of compiling, embrace the compiler. It's on your side, even if it doesn't seem like it at times. And the error messages are incredibly detailed. Plus, the suggestions are usually right. Also, the Rust ecosystem has great tools. Use them. You have Rust format for consistent and automatic formatting, and there's Clippy to lint for common mistakes and suggest improvements. And we have Bacon, tasty bacon, with watch mode for continuous feedback. Embrace the refactoring path. First, make it work. Yep, you can go ahead and clone. Then, make it right and figure out proper ownership. And last, make it fast and optimize those allocations. It's not an easy journey, but stick with it and you'll reap the rewards. You'll have confidence in your production code since Rust catches and prevents all kinds of bugs. Refactoring and maintenance will be bliss compared to other languages. You'll get performance without compromise thanks to compile time optimizations like the borrow checker and high-level zero-cost abstractions. Then there's the excellent tools and ecosystem. Everything you need from linting to formatting to package management, documentation generation, and testing comes out of the box. And to top it all off, industry adoption is growing, so you'll be investing in skills for the future. Yes, there's a learning curve, but it's an investment, not a cost. The compiler is your pair programming partner. It catches bugs you'd miss. Once you get it, you'll wonder how you lived without it. And welcome to the cult of the crab. Right, let's walk through converting our Python chat app to Rust. Although to be fair, it's more like rebuilding it in Rust. So first things first, we're in our project stir. We're gonna need to init a Rust project. So you would do that with cargo init, and in this case, we'll call it like hello Rust. Rust. Okay, so that did that. I'm actually going to get reset because I've got the diffs to smooth this along. So get rid of that. See ya. All right, and then we can take a look. So we do cargo init. So now we have a blank Rust project. Literally blank. We've not done anything to it. And in fact, we're going to want to add a get ignore. Get ignore. Okay. All right, so looking at the diff now, get ignore, that's just ignoring the generated files. And then we just have our cargo file with no other metadata and a hello world. And it is freaking out because I need to reload my workspace. So you can see here the VS Code plugin is failing because it's in a subdirectory, and that's atypical. So let's go ahead and add some VS Code settings. First things first, let's go ahead and commit this just so we can have the diffs. Ta-da. Normally you would not need to do this if you had your project in the top level. In this case, again, it's only so that it works as a Rust project within a nested directory. So you can see here, it's looking for our cargo file in this nested directory. And now cargo and Rust Analyzer should be happy. So let's go ahead and commit that. Again, typically you would not do this. Okay, let's add a basic README. Let's also, while we're at it, let's go ahead and add some basic dependencies, and I'll walk through them. Let's add some basic dependencies. We had the README. So what we have added here is anyhow, like we said, that's a crate just to make error handling easier. It'll squash all error types into one. We also have Axum, which is sort of like Flask in a way. Tokyo is the, at the moment, kind of reference implementation for async in Rust. Yes, it is defined through a crate. It's not in the standard library at the moment. And then tracing is how we're going to be logging things, and you'll see that in a second. So we've got our basic dependencies. Let's go ahead and commit those along with our README. And if we take a look at our project, again, at this point, still pretty standard, still just hello world. All we've done is just added some dependencies. What we're also gonna do is use the bacon Rust tool. So if we do Rust bacon, it's a way to have it kind of like a task runner. So invite, you're watching for changes. This is a way to do that. So let's do bacon all right, bacon init, and this is the out of the box bacon. But what we're gonna do, so let's stage those so you can see the diff. Actually, run long is already set up. So out of the box, it'll just watch for changes. What we will do later on is add some compile flags so that it compiles with metal and such. But for now, that's all we need. So now we can watch for changes. cd rust 8 bacon run long. So now what it'll do is it will watch our project for changes, and then it'll automatically recompile it for us. So if I go in here, right now it's just going to, once it's done compiling, did hello world, save, recompiles it for us. So this is just a quality of life thing. All right, now let's go ahead and scaffold out our main file and add just a very simple web server. Okay, let's see here. Let's get rid of these, cherry pick some changes to make my life easier. So what do we have here? Well, quite a few changes. Since it's essentially a diff of just green, we'll take a look in the actual code editor. So we're pulling in some packages. In this case, context from anyhow allows you to add like a little helper message when something goes wrong. Result in this case is anyhow's result type. Again, that allows you to kind of squash things down. We're using the router and the get method from Axum so that we can set up a route. And then tracing, you'll see it in a second. This is again just a way to kind of like log info out so that we're able to provide traces. So our main, this is going to look a little funky, but bear with me. So we're going to set up Tokyo as our entry point for async. So async main function, and we're going to return an empty result. The reason why we're doing this is so that we can have our nifty little error propagation question mark handler. If we weren't returning a result, we wouldn't be able to just question mark it away. So if I just do like a void return, it'll throw an error about how it's not returning anything, and then these will stop working, right? Because we need to return a result. So I find that the question mark, the syntax is a lot easier to deal with than just doing matches. So we're going to go back to doing an empty result. Gets us back. All right. So first things first, we're going to set up our logging. And again, all this is going to do is allow you to plug in to this tracing, and we're going to do info. And then we're going to have our new router from Axum. We're only going to have one route, which is going to map to the top level, and it's going to call our root function. And it's actually just going to return a static string, in this case, hello world. So no templating, none of that business. We've also got our address. So we're listening on port 3000, and we're going to bind that. So Tokyo is going to listen on 000, which is not 127, because 127 is localhost. 000 is everything, port 3000. And if it fails to bind, like maybe you've got another app listening on 3000, this is what it would show you. And then otherwise, starting, it's ready, and we're serving it. Yeah. So because we have Bacon running, it's automatically going to do that for us. So you can see here, we're running on 3000 and it is ready to go. So if I do localhost 3000, hello world. Cool. Okay, so basic, sort of kind of like we have Flask web server setup that does nothing, but we're making progress. Next, what we're going to do is, actually I'll cancel out of this. In some projects, the way you would handle config is through the environment. And we could definitely do that. We could use an environment file. What we could also do, because we're generating a binary, is use command line arguments. And that seems to be the go-to in the Rust community. The benefit to that is you're not having to move around or set up an environment file. You can just invoke it with different args. So let's go ahead and set that up. If we take a look at our changes now, we added a new package called clap, which is command line argument parsing. And we're going to use the derive feature. I should have gone over those other ones. So Axum, we're JSON and Tokyo support feature flags. And then for Tokyo, we're just whole shebang. So derive in this case, it uses the derive macro to just kind of make things more streamlined, less boilerplate. So command line argument parsing. What's important to understand is all this package does is when you invoke the binary, when you invoke the package or executable, whatever, all it's doing is that string, it's parsing it out. It's not doing anything else. So there's no other fanciness going on. All it's doing is getting the command line args, parsing them, and allowing you a way to read those in. It's not doing any kind of like command line input reading where you're like reading the input and doing anything like that. It's not doing like terminal interface, UI, just command line args. So if we take a look now at our command line arg parser, so we're bringing in claps parser, and we can pretty much see where the diff is. So I'll pop over here. So we've brought in the command line parser requirement. We're going to set up a struct for our command line arguments. So there's going to be 2 of them for now. There's going to be the address that we're listening on. In this case, it's going to be a string for now. We're going to set it to a default value of 000. So if we don't provide this argument, it's going to default to 000. We're also long in this case means it's only going to be available with the long version, so -IP, --IP. Port, on the other hand, is going to have long and short, meaning you could do -P or you could do --port. And in our case, it's an int, unsigned int of up to 16, and its value is 3000. So it's going to default to 3000. So we've got, this is our struct. We're deriving the parser, and we're also going to have our command line helpers here. So no long about, we're going to pull over this from our package, our cargo. And then we're also going to parse the args here on the top of our main. Once we have our args parsed, we can then use them here. So before we were hard coding them, right? So before we were just hard coding the address. Now we're going to format it from our arguments. And then same thing, it still gets passed in as a reference. So now, because we have some default values, we actually don't have to change bacon. But what we can do is, if I do cargo build -- release, yeah, sure, why not? We can take a look at our command line helpers. So it's pretty nice that, again, if you were packaging this up and distributing it, if I were to do target release, hello Rust -H, you can see here now we've got our hello Rust that pulled it over from cargo, oops, and then we've got our arguments here. So IP import, and it's got the defaults. Very nice. But like I said, we've got our default values, so we can go back to just running it as is, and it'll still be the same behavior. It's just now our ergonomics are nicer. Okay, so we have added our CLI args, again, as opposed to an environment file. Right. Another thing we're gonna want to do is add a shutdown handler. So what do I mean by shutdown handler? Well, in this case, what it's going to do is, using Tokyo, it's going to, when you do like Control-C or signal term or whatever, what it's going to do is intercept that, wait for the current process to finish, and then terminate it. So it's just best practice. Again, nothing in our demonstration that's really going to change anything. But again, a little bit more setup, a little bit more cleanup. There's some example in the Axum project you can see. So we're bringing in signal from Tokyo. We are going to add the shutdown handler when we call serve, okay? And actually I'll go back to the diff. Just some commenting, and then our shutdown handler, and this is again just totally ripped from the example. We're gonna listen for the sig, what is it, sig term, I think, Control-C. Listen for that, and then when that happens, it's going to terminate all the stuff. So after the process runs, again, just some cleanup, just some nice to-dos. Add that here, and when I do this, there's no perceivable difference because there's not a process running. Actually, am I running bacon? Yeah. So there's no perceivable difference, but in theory, let's say you were doing some generation. What it could do again is just wait for that to finish and then kill it, as opposed to just failing it right away. All right, let's go ahead and add some API Docs generation. So we're going to use and I'm going to butcher this, Utoipa, I want to say it as Utopia. I know it's not, Utoipa, I think, sorry, package, and it integrates with Axum. So number one, this, and then also the Swagger UI. So I'm using Swagger UI because it's able to be bundled into the binary without any CDN dependencies. So we're adding this package, and then it's actually pretty easy to get started. So we can see here, pretty simple. Taking a look, we're going to depend on these two. So Open API spec, Swagger UI. We're going to have our base API docs struct. So in this case, simple description, some basic information that'll show up on the main docs page. And then we are also going to API docs and then annotations. All right, so in our main, we're going to create our API docs, and then we're going to add that as a route here. So /API docs, the package is going to handle the JSON generation for us. We just have to map it. So it's /API docs, it'll be available. The package is, the crate's going to handle the generation for us. We're passing in our struct, and then we go down here for our route. What we did is we added this information here. So it's a get, it's on the root, tag hello, I'll show that in a second, and some basic information. So now if it's running, it's going to need to compile all that stuff. If we go back here, so nothing changed there, but if we go to API docs, nice. We can see here now we have automatically generated our API page just from our code. So this tag here, tag hello, that's what this is. So it's kind of like you're able to group your different endpoints together. That'll come in handy later. In our case, there's really no parameters, nothing too fancy. We can try it out, but it'll just return a string. But yeah, so API docs generation. What's really helpful with Axum and Rust is on the payloads. So both on the response side, but even more so on the request side. When you define your payloads, when it's parsing it, it'll ensure it's the right type. So if you say, it's a parameter is a string versus a float, it'll actually ensure that the requester submitted the right types. So not just the shape, but also the types. So I find that really handy that it does that just out of the box using the type system. One other thing that I have as a quick note is Clippy. So I've got Clippy running as opposed to just check. So it's pretty strict, but that's a good thing. I'm trying to think what would be a good Clippy lint. Well, it'll almost certainly come up, but basically what this setting is just to mention that in my VS Code, I've got Clippy running instead of just check. All right, next up, let's go ahead and add some templates and error handling. All right, so quite a lot going on here. If we take a look at our cargo, we are going to add two dependencies. Askama is like Jinja, but it has compile time checks for the templates. That's pretty nifty. And then Tower HTTP, which is going to allow us to do some middleware for error handling. Starting from the top, again, we're pulling in our tower. Actually, also, we're going to be serving CSS from a directory. Okay, so Servder, let's come back to our controllers and our templates. Let's just see if there's any other changes. So we are So we've added a middleware to handle static. So there's going to be a static directory that we're going to serve from. We're also going to add some handlers for 404 and error. So there's going to be an error controller to handle like 500s and also handle 404s. In this case, starting, yeah, it looks like some formatting changes, so nothing too big there. And then our root is gone because we're no longer just doing hello world. So changes, let's take a look at some of these other directories. So our static directory is just gonna have some basic CSS, nothing too major there. So we're serving from this directory. Okay. Then we're also gonna have a templates directory. And in this case, it's gonna be Jinja-like, but we're also gonna have, remember, it's Rust, so it's gonna have compile time checking. Yeah, so we can see here, it's actually gonna, we need to specify the sum. We're gonna have, like if we take away this end, this when, we're gonna get a compile time error. It'll say we're not checking all of the, yep, we're not checking all of the branches. So you can see here it's actually exhaustive. So templates don't trigger bacon, but you could see there when compiling it actually did force us to check everything. So that's pretty nifty. So we've got templates. One is just our standard page where we're outputting the content, and then the other is our layout, basic stuff for scaffolding our CSS, and eventually we'll have some footer stuff, but we've basically just got a place to put our content. So this is the actual templates directory for the template files. And if we take a look, it's top level. So we've got our source for our Rust code. We've got our static directory for CSS and other static assets. Target is where our compiled code's gonna end up. And then templates is a top level for our actual template, Jinja template files. So if we take a look, our main in source, we've got now controllers and templates. So there was the template files, and then we also have our template, like template structs for some of the wiring things up. Let's go ahead and take a look at that. So we have a templates mod. We're going to module, and we're gonna have some dependencies here. So we're gonna have a page template struct. And this is gonna be our main template. So it is, if we go back, we can see that the page template extends layout. So we don't necessarily need a layout struct. So page template, the path is from the templates directory, so page, we're deriving the Askama template macro, and we're just gonna have two fields. So title and optionally some content. So then we're gonna have an example code here from Axum. It's quite involved, but just bear with it. So HTML template renderer is gonna take a generic, and then we're going to implement into response, which is a Axum thing. So convert it into an Axum response for the template renderer struct, where the generic is of type template. And then into response is just going to call when it's okay. It's going to get the HTML markup. And then when it's an error, we're actually gonna throw a 500, and then we'll take a look at our error handler in a second. So this is example code from the Axum project. Again, it's using generic, so it's kind of hard to grok at first. But this is how you would go from, your controller response to the template response. This is the code that wires it up for Axum. Let's take a look at our controllers. So we've got top level mod file. That's just declaring our chat and error modules. And if you see pub crate, that's just a way to say that basically these are fair game for within our crate. So not totally public, so it couldn't cross over into another crate's boundary, but within this crate, it's totally fine. And this is typically the default visibility I'll use is pub crate. Let's take a look at our error handlers first. So these would run either on 404, and if we take a look at main, so on error is obviously when there's ever going to be an error, or if all else fails, if it can't find a route, then fall back to 404. So we're going to bring in quite a few dependencies. We're also going to use our page template struct from the templates module. So you can see here, starting at the crate, go down into templates and pull in page template. We're going to have this handle errors function that is just kind of like our entry point. So it's going to get the request and the next, so like the next handler from Axum, although I guess in this case it is layer. Yeah, it's from Axum. And what it's going to do is get the response. It's going to check it. So if the response was an error, go ahead and handle that. In this case, 500. Handle it. We could break out other error types as well. Stay tuned. And then otherwise, just let it go about its merry way. Don't try to intercept it. So if it's an error, specifically internal error, we're going to jump down to this 500. And then what we're going to do is render the page template. And specifically, we're going to say error, there was an error. And then return a 500 error code along with our markup. And that's how we're getting, again, going back to into response. Okay, so that is for 500s. And then for 404s, which again is our fallback. So if nothing else is able to run, or if like nothing else, if the router doesn't match for any of those other things, it'll end up here. And all it's going to do is render our page template with a not found, and then send a not found status code. Yeah. So we've got status code and markup, and this is our tuple where we're returning. So those are the error handlers. And that's again how we're going to do 400 and 500s. Let's take a look at chat super quick, and then the chat controller, because it's basically just the hello world. And then we'll try out some of those error handlers. So we've got our chat module, similar to what we had before. We're going to have our API Docs metadata. And then all we're doing is just rendering the page template with a hello world message. So now if we go back, let's reload it. We can see same thing. The API docs have been updated. And then if I go here and just do that, now we can see we're rendering with our style sheet. We're rendering with this. If I do something like that, okay, not found. Okay, so we've got some basic templating. We've got some basic routing. What we're going to do next is add some models. So sort of simple ORM type stuff. We had previously, we were using Flask and SQL Alchemy. Now we're going to be scaffolding up quite a bit. Let's take a look here. So let's look at our top level cargo. We're going to be setting up some workspace crates. So I'll get to that in a second. In terms of our dependencies, we're going to be adding SeaORM, which is seems to be a popular choice for ORMs. There's also Diesel. In this case, SeaORM take your pick. They both seem great. I just went with SeaORM because that seemed to be the top of mind for the community at the moment. So SeaORM with macros, with Tokyo, we're going to be using SQLite actually. JSON, UUID, and then migrations. There's a little helper crate from yours truly. And then we're going to be using CERD for serialization. And then also there's a package here, this error. It's by the same author that did Anyhow. So whereas Anyhow is useful for like binaries and it's useful for kind of collapsing errors down into one to make it easier. This error, on the other hand, makes it easier to define your own error types and remove some of the boilerplate. So it's not about collapsing errors down into one, it's rather about making it easier to express your own errors. Quite a bit different cargo structure. So we've created a workspace. So this is going to be our top level workspace. We're going to have our own main crate, and then we're also going to have a migration crate and an entities crate. So migration is where we're going to scaffold or set up our actual SQLite database. And then entities is where we're going to have our models and our logic, business logic, that kind of stuff. The reason why they're separate is it makes it easier to do dependencies and things like that. So we're going to define all of our dependencies basically at the workspace. And then for these subcrates, we're going to just inherit them. And then, yeah, we can see here we have local. Okay, so that was quite a lot for our top level cargo. Git ignore, we're just going to ignore our SQLite file. README, yeah, we're using SeaORM. Let's take a look here at our new workspace crates. So before we just had our one source directory, and that was for our one project crate. Now we have migrations and entities. So if we pop into the migrations crate, which again is going to set up our database, we can see here we're going to depend on SeaORM and Tokyo. And then we're also actually going to depend on our entities crate. Our entities crate, again, it's just going to have our basic models and that type of stuff. So you can see here, we've got our dependencies getting pulled in from our workspace. And if we take a look at our lib file, it's just going to be defining all the child modules. The error, this is what I had mentioned about this error. So you can see we can derive this error. And again, it just cleans up some of the boilerplate that you'd normally have to write out by hand. In our case, we're going to define a database error, enum. So for example, not found, chat not found, database error, serialization error. And the reason why we're doing that is because those are different errors, right? If we're not able to find a user versus we're not able to find a chat, that actually means something different. If we were using anyhow, they would all just kind of get collapsed into one, and we wouldn't have as much meaningful information. So we're defining our own error type. And then we're also going to have an app error, which is going to be like our status code and our message. And we've got some wiring up here. So into response, similar to that template, right? Where we're going to return the message and the status code. And then we're also going to convert from database error to our app error, because the app error is what we're going to return from our controller. You'll see in a second. So if we have a database user not found, we're going to return a not found, user not found. Same thing with chat not found, chat not found. But if we have these other errors, we're going to have a 500s and then different message. There's probably ways we could kind of clean this up and streamline it, but you can see here, again, these are different. They mean different things, right? If we just had a 500 for everything, well, chat not found, that's not really a 500 error, or user not found, that's not a 500. It is a 404. So this is why it's helpful to have our own error types. And again, what we're doing is we're converting from the database error into our app error. And then the app error is just a simple structure that we're going to return from our actual controllers. So just some helper code here to do our error handling. Our actual models themselves are pretty straightforward. So let's take a look at probably chat first. Yeah. All right. So there is a gotcha here. We're pulling in quite a lot of dependencies, SeaORM, some utils to kind of clean up things, serialization. We're using our database error. So here's the gotcha. In SeaORM, because it uses macros and it's dynamic, it assumes that your struct is called model, and it has to be called model from what I can tell. The problem is when we're generating our API docs, if everything's called model, it clashes. And I've really tried quite a lot to, do something funky where I'm like importing it as and aliasing it and doing all this kind of stuff, and it just didn't work. So for right now, the simplest answer I have is just to basically duplicate the struct for every model. One is for the schema, for our API docs, and then one is for the actual model, for our business logic and our code. So that's why these are duplicated. I plan on revisiting it, but for right now, that's why there's two. So wherever you see schema, that's for our API docs, and wherever you see model, that's for SeaORM, that's for the ORM. So we're gonna have a chat with an ID. We're gonna also have a UUID. For SQLite, for simplicity's sake, I'm just going to use a string. You could also store it as binary, but for right now, we'll just do string title. For the created updated, we're going to use a datetime UTC. And then for the API docs, we're going to say it's a string, but it has a special format. And then similar for the model itself. Here, I just have a little helper macro for my SeaORM utils crate. So all it's doing is just, again, simple macro I whipped up just to cut down on the boilerplate. So all this is doing is just going to add in the UUID and timestamp. So let's see here, go back, go to def. And you can see here, it's just going to add in some setters, getters, that kind of stuff. Well, in this case, setters. Just cut down on boilerplate because that's going to be common across all of the models. We have our relation. So we're going to have a chat, and it's going to have many chat messages. Okay, easy enough. We're also going to have another macro here from my helper crate that just, again, cuts down on some of the boilerplate from SeaORM. And then another macro to have the through relationship. So a chat is going to have users through a chat user model. So a join table. So in this case, it's to via some intermediary table. So chat has chat messages, has many, and then chat also has chat users through the chat users model. We're also going to have, before we save, so this implementing the active model behavior, before we save, we're just going to update the we're going to set the UUID first time, and then update the timestamps. So again, from my helper crate, if it is an insert, create the UUID, set the created at, and then for both insert and updates, go ahead and set the updated date. So you can see here, this is just a little helper to cut down on boilerplate. Okay, next we're gonna have some helper methods that if you're coming from, Rails or any of these other ORMs, I should say active record, just some helper methods. So we're gonna do find, which is, you can see here, gonna return a result or an error. So this get is going to call find, and then if it's okay, extract the record out, or if not, throw an error. Find by UUID. So instead of by ID, it's going to be the same thing, but with UUID. Same with get. And then we're going to have some helpers to get the associated messages with this chat. So you can see here, find related, all, and then await. We're also going to have some helper to write it out to JSON or convert it to JSON. So first things first, we're going to get our associated chat messages. We're then going to call the to.json on them. We're then going to create our JSON for the entire chat. So it's going to be title, ID, UUID, created, updated, and then the nested chat message JSON, and then return that. We also have a helper just to create a chat message associated with this chat. Again, it kind of improves some of the ergonomics. You can call like chat.createChatMessage. So you're going to paste in you're going to provide the DB connection, the content, the user ID, and the state. This will all make sense when we get into the chat message. But yeah, basically it's just some helper methods. And then lastly, deleting all chat messages. So chat has quite a lot. Taking a look at the chat message, same deal with the, well, in this case, actually, we have a role. So it's going to be assistant, system, user. This kind of lines up with the different types of messages from the OpenAI API spec. We're also going to implement the display trait for our role, so that we can, convert it to a string and stuff like that. So we have these different types, and then we've also got these, we're matching. So when it's assistant, it's, assistant string. This is helpful for converting to JSON, for example. We've also got a state. So the message could be pending, loading, ready, error, and then same deal with the display trait. And then I think the only thing under the hood is we are storing it as a string in the database. Okay, same deal as before. 2 different structs, one for schema, one for the actual model. I don't think there's anything really fancy here. Pretty much the same deal. In this case, we've got some options. We're pulling to our role and state. We've got our foreign keys. We've got, again, that UUID timestamps helper. Our relationship, so it's going to belong to a chat, and similar stuff with cascades. It's also going to belong to a user. So a chat message can belong to at most one user and at most one chat, whereas obviously chat can have many. And then just again, a helper macro from our handy little helper crate, utils crate. Cut down on boilerplate. And similarly, helper to, do the UUID and timestamps logic. And then for chat message, the only thing we're implementing as a helper is just the to.json. And that does it for the chat message model. Chat users is a very simple join table. So you can see here, all we're doing is just going to have 2 columns, one for chat ID, one for user ID. And all it's doing is just, again, it's a join table. So it's able to provide a many-to-many. And yeah, pretty standard stuff here. Nothing really to go over. Lastly, the last model is our users. So similar to chats, we've got our schema, we've got our model. Again, I don't think there's anything too much here. We have the chat messages, has many chat messages, and then chats users, helper macro, UUIDs timestamps. We've got some helpers here. So find first, in our case, you typically wouldn't do this, but just for demo purposes, just find the very first user, because in our seeded data, there's only going to be one. So just a handy little helper. We're also going to have the get the default chat. I should point out that then in this case, this is a function on the actual model itself. So notice that the first param is the DB connection. And then this get default chat is on an instance. So it's on an actual record. So you would do like user find first user, something to that effect. Whereas this one would be an actual instance of a user, get the default chat. And in this case, this is just going to pick the first chat because for our seeded data, we're only really going to have one. This is also going to have a lookup. So to get a user specific chat by UUID. So find related given the UUID. Okay, so those are all of our entities. And again, this would be kind of like SQL Alchemy, but we obviously need to create a database. So that's where this migration crate comes back in. So if we take a look here, this would be scaffolded out by SeaORM. So you can see it actually already ran. SeaORM has a utility that you can use. So it'll generate this for you. There's really, this is scaffolded by SeaORM. What we're looking at is our specific migration file itself though. So we've got a few tables here: user, chat users, chat message. Columns are going to be as you'd expect. We're going to have a migration struct, and we're going to implement the migration trait for it. So when we call up, we're going to create the various tables with the appropriate columns. We're going to be taking a look at our chat users. Chat's users, we're going to be setting some indexes and foreign keys. For chat message, same thing, setting the columns. I don't think there's anything fancy here. I mean, sometimes you need to put nullable, foreign keys, and then afterwards creating more indexes on the chat message table for chat ID, user ID, role, and state. So creating more indexes. Then we're also going to have a helper function here to seed the database. So we'll come back to that. And then for down, it's just going to be the opposite. We're just going to drop those tables. And then for seeding, what we're going to do is we're just going to create some test content. So in this case, a test user, a test chat. We're going to insert those. And then we're also going to set up the user's chats relationship. And that would be our migration. So we actually, in our main code, we actually check the DB and it'll actually trigger the migration automatically. So if we take a look here in main, somewhere in here, main DB connection, what it should do, you can see here, open DB connection, and we're passing in, we have an arg. We're going to use the app.db, so that'll save it in our project. This RWC seems to be something I found in the GitHub issue queue. It seems to be needed, at least for me it was. We're going to also import those schemas we had mentioned from our entities. So those will show up in our API docs. And then for now, that should be it. So we're not having any scaffolding for our controllers just yet, but we are wiring them up. So if I do bacon run long, okay, so you can see here it's warning that we have an unused And there's Clippy. We have an unused variable for now. And because we called our migrator automatically on the first time, it went ahead and created it for us. So if we go ahead and open, we can see for our app.db file, which is now here, we can, let's see, generic diagram. Right, we can see we've got our new tables. So user, chat, chats users, chat message. And we've also generated our seed content. So we've got a test user here, test chat, and then the relationship between the two. Alrighty. Now, again, we've wired this up, but we don't have any controllers or any logic. So let's see if we can fix that. So first things first, let's commit this. And now let's start implementing some of our actual logic. And it's running through Rust Analyzer. Clippy's angry for a second. All right. So we added some workspace dependencies because we are going to be serializing some stuff, but no new actual packages. Our main looks quite a bit different. Looks like mostly formatting stuff, although we did add some state. Right, exactly. And we're going to have some controllers here, and we're cleaning some things up. So let's see if we can break this down. Okay, so our templates, why not? Just added some simple username stuff to the template. That's the only thing there. Our main, what we tried to do was kind of simplify our main a little bit. So if we take a look at our app module, we've got a logger, DB connector, listener, shutdown signal, all that stuff that was a main, we're just setting it off to the side in here. So that's where it's been moved. We're going to be using app state, which is a way in Axum to kind of, access things across requests. So in this case, we've got our current user and a DB connection. So that's going to be our app state. And again, we've updated our API docs a little bit. We've also got a helper type. We're going to be commonly referencing app state. And so extracted app state is just state arc app state. And arc is a type to handle like thread safe. It just increments a counter, it's a pointer, commonly used. So just two helper types that are just type aliases. All right, our main is pretty standard here. We're just going to, like before, set up logging, parse the args, get our database connection. We're going to set up our router here, and that's where a lot of the logic has been moved to. So when we get our router, we're just going to pass in our DB connection. Then we are going to use that find first user from our model, that helper function. We're just going to pick the very first user because for demo purposes, we only have one. We're going to create our app state. And in this case, we're going to have our DB connection handler and our current user. And that's going to get wrapped in an arc reference counter. We're going to have our API Docs struct that we're generating. And then our router. So we've got our top level index handler. We're going to have a chats path We're going to have a top level one. We're also going to have a specific for a given chat, show it. We're then going to merge in our API docs routes. We're going to have our static handler, error handlers, fallback handler, and then the tracing. So this is a little bit different, but it's a way to handle tracing. And you can see in here that that's what all this stuff is. So the router is pretty much the same. Templates, I think, are the same, looks like. And I'll just take a look at the div. Yep. Error handling, yeah, error handling is definitely different. We already went over, we're adding a username to our page template and then username to our page template. Looking at the error controller and chat controller. So as I had mentioned before, the error handling previously was just one or two things, 500 error, 404. What we've gone and done is actually beefed it up so that we're more comprehensive. So it's a little bit different. We've still got our status code and we've still got a title and body. So that's what this is saying. And then we're going to create a hash map. So given a status code, you can kind of look up the body and the title. So we've got all of our status codes here, bad request, unauthorized, well, most of our status codes, I should say, the ones that we're going to be dealing with. And then what that means is instead of having to have a helper function for each of the status codes, we can just, again, pluck it out using that hash map. So we can see here, handle error, we're going to have a pull out the title and body from our hash map. And then we're going to pass it into our handle error with template, which again is just going to render our page template with the right status code and with the right title and body. So this is, again, just a way to kind of clean up that boilerplate. In this case, our fallback is mapped different in our router. So that's why we have it split out like that. We've got our error handling middleware and then our fallback, which is just basically going to do the same thing. We're going to get our 404 status code, pull it out from the hash map, and then call handle error with template. So both of these are pretty much using the same thing. So now we've cleaned up our duplicated logic between the error handler and the 404 handler. And we're also, again, just mapping quite a few more of our error codes in a hash map. So error handling is cleaned up a bit. And then for our chat handling, this is going to look a little different as well. So we are going to have our API docs. Let's actually pull that up while we're going through the / API docs. So we've got our, and this is why we went through the pain, we've got our schemas in here so we can see a role can be of the following types. A message has all of these properties. State can be of one of these types. A chat has these properties. And then a user has these properties. So again, that's why it's nice to have this rich type system that Rust provides us. Is again, you kind of get this right here, and it's going to actually be checking this. And then for our chat endpoint, so we're just going to really have one, and we're going to pass in a UUID to get the actual chat. So this is our API docs. The index function in this case, all it's going to do is redirect to the default chat. So this is, again, that helper for our user model. We're just going to get the very first chat that we have on file because we're only using seed data, and we're going to do a redirect. And then for our actual chat show, we're going to look up the chat itself. And then actually, no, for this point, we're just doing hello world. So we're not doing any lookups just yet. So we're going to redirect, and then we're just going to show a hello message. So let's take a look. So it happened pretty darn quick there, but you can see if I put in top level, it's going to redirect. And same thing for this. So it's just doing a hello message. And you can see here, this is where our trace is coming in. All right, so we've got some, again, basic app functionality. And now let's go ahead and add an actual chat component. So we're going to bring Svelte back into the